Hello, and welcome to our next chapter of thermodynamics. In this chapter, we're going to be looking more at entropy and the third law of thermodynamics. We've covered the first and second law. And what this law comes down to is thinking about how can we calculate entropy from measured data. So when we talk about enthalpy, that was related to heat, so we have like bomb calorimetry that gives us a way to measure that. And the third law is not directly related to this, but is a tangential part of this question. How could we actually calculate entropy from measured data? So to answer this question, it's going to be a little bit roundabout. We need to do some mathematical manipulation first to understand some relationships between entropy and things that we can measure. And to do this, we're going to be taking advantage of the fact that we can write out total differentials of variables that we have encountered so far in thermodynamics. For example, du, right? If we take u and say, okay, well, u is a function of the volume of gas that we have and the temperature, we can write a total differential just based on the rules of partial derivatives, that the total differential is the partial derivative of u with respect to t, and constant v, I'm just trying to keep the order the same as my notes here, plus the partial derivative of u with respect to v, a constant t, dv. This is just definitions, right? So there's no thermodynamics involved here. This is just a purely mathematical. This is the definition of a total differential written out in terms of the partial derivatives that are part of it. Where this becomes useful is we can also find other ways of expressing du. So in your homework, you're going to derive this relationship, that du is equal to T ds minus P dv. And what this comes from, this is the reversible work, reversible heat, and the reversible work. So if we consider this for a reversible process, we can get an exact relationship here. And then since these are all state functions, it doesn't matter what the exact process is. This is still generally true. And so we can start to make some relationships here. Right, we have something involving entropy, and we'd like to rearrange and figure out. So we can set these equations equal to each other. So we can have du dt at constant v dt plus du dv at constant t dv is equal to T ds minus P dv. And now we can go ahead and rearrange and solve this for ds, right? We'd like to get ds by itself. Okay, so we can say ds. So we're going to have to add P dv on both sides, and we're going to have to divide by temperature on both sides, over the whole thing. Okay, so overall that's going to get us an equation that looks like this. ds is equal to du dt at constant v times 1 over t dt. And then we'll have two terms that involve dv, this term and this term. We can combine them. So we'll have still the divide by t part, 1 over t, plus we'll have our pressure, and since this gets added, it'll be positive on this side, and then this partial derivative here, plus du dv, it's hard to keep all these variables straight, at constant t, all this times dv. All right, so we've got this expression here. This may not seem very useful, but we can do the same thing as we did here with du, where we wrote out the total differential. We can do the same thing for ds. If s is a function of temperature and volume, we can say, okay, ds is equal to ds dt at constant v dt plus ds dv at constant t dv. And now we have a relationship here. We have two things that look very similar. We have a dt here. We've got dv here. And so the stuff in front of these differentials is the same, is related. So but the second one isn't as useful in the green, but the one in the red is the one we're looking for. It tells us how S changes as a function of temperature if the volume is kept constant. And that's something we can do. We can vary the temperature of something and make some measurements as we vary temperature to give us some information about S. So we can say ds dt at constant V is equal to du dt at constant V divided by T. So that's this here, just writing in a slightly different way. And the last thing we can just note here is that the change in internal energy at constant, the change in internal energy is a function of temperature at constant volume. This is what we have defined as the constant volume heat capacity. So we can say that the change in entropy with respect to temperature at constant volume is equal to the heat capacity divided by temperature. Now, in general, this is not constant or as a function of temperature. We'll have to, this will have to be measured as a function of temperature, but that's the measurement we can make. If we can do this at constant volume, then if we wanted to find a change in entropy, we can integrate. So we can say the integral of ds dt at constant volume, dt, we go from t1 to t2, is the same as the integral from t1 to t2 of cv over t dt. Now cv, again, is a function of temperature. And that'll be equal to S2 minus S1, or delta S. What's the change in entropy from temperature 1 to temperature 2? Okay, so that gives us something we can measure at constant volume, if we can do this experiment at constant volume. In the next video, we'll look at the more often used situation where instead of doing this at constant volume, which is a little bit hard to do, we do it instead at constant pressure, and we get a slightly different expression, but very similar to the one that we just derived.